This video gives you your first look at vector fields. Now we've already studied this equation extensively. This is called the state equation, and it defines the change, x prime, in terms of a function of the current state, f of x. Let's start our examples for vector fields in one dimension, in which case we just have this single equation for the state equation. Keep in mind that the state is x, and that's a one-dimensional object. Likewise, the change x prime lives in what's called the tangent space. You'll learn the reasons why that's called the tangent space once we study calculus. For now, I want you to focus on the fact that in this one-dimensional example, the state is a one-dimensional object, and likewise x prime, the change vector, is also a one-dimensional object. Now, when we have two one-dimensional objects and we want to look at them both at the same time, that would mean that we're going to look at something that's in 1 plus 1 or 2 dimensions. That's why it was easy for me to create this graph where I have the horizontal axis representing the state, x, and the vertical axis representing the change, x prime. For this, in blue, I've graphed an example of one of our common ecological models called the Logistic growth model. Now keep in mind that a subset of this, if I hide this term right here, is the exponential growth model, where f of x, or x prime, is equal to rx. That's our classic feedback model, where we have a constant per capita growth rate, which is r. But exponential growth cannot go on forever if you have some sort of limited resource or carrying capacity, and that's why we add on this extra term where we're multiplying the exponential growth Rx times a term that says what proportion of the resources are currently free to still be used. You see here, x over k, that's the proportion of the resources k that are being used, and so 1 minus that is the proportion that's still left over to be used. So multiplying the Rx times that leads us to a model where you have that classic logistic growth. Let me draw a little time series, which you may have seen before. If I was going to draw a time series graph of this, where the horizontal axis is time, and the vertical axis is the state x, then starting with some small value of a population, at first it would look like things are growing exponentially, but once we start to butt up against the carrying capacity and the x is kind of using up its limited resources, then the population tops off, and eventually we have this equilibrium where the population is pretty stable, and that occurs when x is equal to k. In this logistic model, k is the carrying capacity. Okay, so it's nice to have a time series on the board for a little bit so that we can contrast it with the other thing that I've graphed. This is not a time series. This is a very special type of graph that we're only able to visualize in one dimension because we're trying to compare how the rate of change, x prime, depends on the current state, x. Because both of those things are one dimension, we're able to construct this two-dimensional graph that shows x prime versus x. Okay, but what's a vector field? As you're going to see in higher dimensions, we're not able to see this graph anymore because there's just too many dimensions going on. And so this is not the vector field. What the vector field is in general, no matter how many dimensions you have, the vector field is the state space itself, but then with these little arrows overlaid on top, and those arrows represent how quickly the state is changing in time. In other words, there's going to be little arrows that I'm going to draw on top of this state space, and those are going to be the values of x prime, the rate of change. So I'm going to draw all those things in blue. So the blue is to emphasize that I'm drawing components that live, I'm drawing objects that live in the tangent space as opposed to the state space. The tangent space is the place where the rates of change live. Okay? So even though it's nice to have this graph, we're not always going to be able to have this graph with us. And so I've drawn it on here as a learning tool so you can see how I take the information in this graph and use it to create a picture of the vector field for our one-dimensional example. All right. So what I'm going to do is I'm going to choose some spot on this state space graph. Let's say I choose this little spot right here. And then with my blue pen, I'm going to draw a tangent vector that represents how quickly the state is going to change in time. I'm going to try to represent its rate of change and overlay it on the state space. I'm going to overlay pieces of the tangent space in blue on top of the state space in black. Okay, so if I pick this point right here, where you're going to see x is just a little bit greater than 0, I want to draw a little arrow that represents x prime. Luckily, I have this graph right above, so I can see what the value of x prime is for this equation. But if I didn't have this visual available, what I would do is, let's say that this is the value of x is like 3.5. I would take that number, 3.5, for the state x, and I would plug it into f of x. It's going to be the input value for f of x, and then given specific parameters for r and k, if I had values for those, parameters, I would be able to take the chosen state of x that I'm picking here and plug and chug into f of x, and then I would get the value of x prime out. Luckily, this picture right here kind of gives me a geometric representation of doing that for all values of the input x, and so I'm just going to use this handy-dandy graph to start overlaying vectors of the tangent space onto this state space. Okay, so again, I'm going to pick this small value here of x, and what kind of tangent vector do I have when I plug that into f of x? Well, I have a positive number up here. You can see that x prime is above the horizontal axis, so it's a positive number. But it's not the biggest number we have. It's kind of a smaller number. And so I'm going to represent that like this. Okay, so you can see that I've kind of drawn a vector. Remember that a one-dimensional vector is really just like a number, but it still has a magnitude and a direction. And so the magnitude of a one-dimensional vector is its absolute value, so it's kind of like how, big in absolute value that number is. And its direction in one dimension is its sign, whether it's positive or negative. Because I know this is going to output a positive small number, I'm drawing a vector that is little and it's pointing to the right. That represents its positive value. Now, as I move along in the state space a little more, you can see that the values from x prime are getting larger and larger and larger as I approach this peak. Coincidentally, it just happens that the peak in this logistic model will always occur halfway between 0 and the carrying capacity. So this peak really occurs right at k over 2. Okay? So as I approach that, my vectors are getting bigger and bigger, and so that right where I have this peak right here, I'm representing it by a vector that's still pointing to the right because x prime is always positive in this range right here. But you can see that I've been making the arrows bigger, and that's because this output for x prime is getting higher and higher as I get to this point. Then once I go past that point and I'm starting to approach the carrying capacity, you see the output from f of x is getting lower and lower. And so likewise, when I draw my tangent vectors, they're going to get smaller and smaller and even smaller, because really when I'm at the carrying capacity k, the output, if I plug in k into f of x here, you can see it's actually a root in this quadratic equation. In this down-facing parabola, the roots are 0 and k. And so at both 0 and k, the representation of x prime is just 0. So I'll represent that by just putting a dot there, because really the rate of change is equal to 0 when x is equal to k. The rate of change is really tiny over here, and when x is equal to 0, the rate of change is also 0. So I've got the two dots going on there. I'm actually going to make them a little bit bigger here, because these are really, really important dots. These are really important points. As we move on further, you'll see that we're going to refer to these as the equilibrium values. Why would I give it such a funny name? Well, remember, This all goes back to time dynamics. Even though time dynamics are not visualized in the state space, really the story is being told in the time series space, where time, the independent variable, is located on the horizontal axis. And like we were just saying, what happens in logistic growth is that we kind of experience an exponentially growing upswing, and then once we get past this inflection point here, things start to top off, and eventually the population is around the carrying capacity, and it stays around the carrying capacity, and it doesn't move around much, which means that it's at an equilibrium, which means its rate of change is 0, which is exactly why I drew this dot right there, because the output, when you plug in k into this equation, is x prime is equal to 0. If we continue this story a little farther, you see I've drawn the f of x from here a little bit past the carrying capacity, and what happens is that this curve goes up, it goes down, and then it crosses the 0 mark and it starts to become negative. And so what that means for the state space, as I'm trying to overlay tangents on the state space, is that if x is larger than k, if I plug in a value of x that's greater than the parameter value k, the output from f of x here is going to be a negative number, seen geometrically as below the horizontal here, and the vector that I would draw on the state space to represent the tangent would be pointing to the left. Because in one dimensions, the tangent space vector only has two choices for its direction, either pointing to the right when the output is positive, or pointing to the left when the output is negative. Boy, it was really nice to have this handy-dandy graph here to allow me to start to visualize a one-dimensional state space, but how am I going to fare when I start to go into 2 dimensions? So in our next example, as we kick it up a notch into 2 dimensions, the generalized state equations are going to be in this form, where x prime, it has some functional dependence f on x and y. So x prime is equal to f of x and y. And g and y prime, the rate of change for the second state variable y, is going to be equal to g, some function, of the current states x and y. It is totally the same thing that I was doing here. It's just that there's another extra dimension involved. But I really want to emphasize the point here that the rate of change is a function of the current state. And that thing will always continue no matter how many dimensions you have as you study what we're calling autonomous differential equations. So here again, we see that the rates of change, the 2 rates of change for the 2 dimensions, are functions of, now there's 2 functions because there's 2 dimensions, the current states, which there are 2 of, and so that's why you see the 2 functions inside there. Okay, so let's do a little dimension count here. We're talking about having states, x comma y. By the way, I've written them in vertical format here, but you could have just as well written it horizontally as an xy point, x comma y. I just chose to write it vertically so it would fit in nicely. So the state is 2 dimensions, x and y. And likewise, the vector field that we're going to graph itself is also 2 dimensions, x prime and y prime. So the state space is 2D, and the tangent space is also 2D. Remember when we had over here, the state space was 1D, and the tangent space was 1D, and 1 plus 1 is 2, so I could visualize the whole story in this beautiful graph here? Not so lucky anymore, because now we have a state and a tangent space, and so now we have 2 plus 2 is 4. So I wish I had this graph because this graph is really useful, but the corresponding graph like this in a 2-dimensional example would live in 4 space. It would be 2 plus 2D, so 4 space. Fat chance of graphing that one right now on the board. Barely made it through the 3 space thing earlier. So basically, I'm going to restrict myself to visualizing it in the plane, and so that's why I'm stuck just viewing the 2D state space. But what I can do with my blue pen is I can start to plug and chug some points, and then I can overlay the 2-dimensional vectors, the tangent vectors, which are going to make up the vector field, onto the state space. So what I'm going to do here is very much akin to this part of what I did here in 1D, but I am not going to be able to visualize this because the x versus x prime, as we generalize to 2D, this graph would live in 4 space. That's why I don't have it on the board. Okay, anyhow, we can still get this kind of deal, and it's going to look really nice. Let's start to plug and chug so we can get the feel for how you will manually compute the vector field by hand. I know it's going to seem tedious, but this is a really helpful exercise to go through early on in your learning of mathematical modeling because it really cements in the idea of exactly what we're doing when we say tangent vectors are functions of current state vectors. Okay, so just trust me, please, and bear with me as we start to plug and chug some points. Here I've made some little tick marks that are going to represent, here's 0, 0, and here's 1 and 2, and here's 1 and 2 in the y. And so some easy point for me to start with would be the point 2, 1. Okay, so I'm using black for state space and blue for tangent space. So if my current state is 2, 1, that means the x is equal to 2 and the y is equal to 1. So I'm talking about a point that lives in the state space right there. Now, what's the corresponding tangent vector? Well, I'm going to have to compute that using the f of x and y and g of x and y equations that I've chosen for this example. This may look a little bit familiar. This is actually one example of a predator-prey model, which is why I've chosen to focus on just the first quadrant, because in ecological models, oftentimes we're considering the states are populations, and those cannot be negative. You can just as well do this in all 4 quadrants if your states have a domain that's positive and negative. But if I assume that maybe I'm trying to use an ecological example, some sort of predator-prey system where I've set all the parameters to 1, just to make it easy to compute, I would focus on the first quadrant here because my domain for x is just r plus, and my domain for y is also just r plus. Okay? X is equal to 2, y is equal to 1. So what are the values for x prime and y prime? I'm going to compute x prime and y prime right now, so I'm going to use my blue pen. And what I'm going to do is, on the top row here, where I have the 2, I'm going to write out how I'm going to compute x prime. Okay? So x prime is equal to x minus xy. X is 2 and y is 1. So that means that x prime is going to be 2 minus 2 times 1. Okay? You see how I did that? So then that's 2 minus 2, which is 0. And so the x prime component for the vector field at this particular point, the x prime component is 0. Now I'm going to do the same thing for the y prime component on the second line here. Y prime is equal to xy minus y. And so that's going to be 2 times 1 minus 2. So remember, x is 2, y is 1, minus y is 2. And so here I've got 2 times, oh, sorry. Oops, I made a mistake. Probably good to catch it on video because when you start to do this by hand, you're going to have a lot of mistakes. Do this in pencil. Can you see my mistake? Yeah, when I was trying to plug this in, I'm trying to say x, y minus y. So x is 2 times y is 1 minus, that should be a 1. Right, because y is 1. Mistakes happen. It's good to double check your work to make sure that we get everything figured out correctly. So really what I have there for the y prime component for this point is 2 times 1 minus 1, which is equal to 1. And so the tangent vector, the value of the vector field at the point 2, 1 is equal to 0, 1. Good thing I'm getting comfortable drawing xy points as vectors in the plane, because this is really when you want to start drawing it as a vector. Vectors have a magnitude and a direction, and that denotes the strength and the direction of which way the change is going, right? Like when we saw in the 1D, when x prime is positive, x is growing, so things are going to the right. When x prime is negative, the rate of change is negative, and so things are moving to the left. Whenever we compute these vectors here for x prime and y prime, we're going to want to draw them with the arrow so that we can see their directionality. And so it has 0 for the x component, so that means it's not pointing right, nor is it pointing left. And it has 1 for the y component, which means that it's pointing upwards rather than downwards. And so that's an example of how to draw the vector field just at that point. Let's try that again to make sure we've got this down. Instead of 2, 1, let me try the point 1, 2. Right? So here I've got x is equal to 1 and y is equal to 2. And so the point 1, 2 lies right there. Then I'm going to get out my blue pen because I'm now going to use f and g to compute the vector there. So the rate of change, let's see if I can follow this along. For x prime, x is 1 and y is 2. And I'm going to do them both at the same time. Now for the y component, the y prime component, x is 1, y is 2, minus y is 2. And so that leads me to believe that my vector at this point is going to be minus 1, 0. Okay? And remember that I chose this black point in the state space as the values of x and y to use as the inputs into f and g in order to obtain the output for the rates of change x prime and y prime. So when I get this vector out, I'm going to start drawing the vector with its little butt on the point that I chose, and then I'm going to point it in whatever way it tells me to. Here it tells me that the x component is minus 1, so point it going 1 unit to the right. And the y component is 0, so it's not pointing up, nor is it pointing down. So really, you're going to get a vector that looks like that. Hope you're starting to get the hang of this. Let's just try this one more time. Maybe I would like to pick a point like 1, 1, which is right smack dab in the middle of my whole thing. So here's the point 1, 1. And again, in order to compute the vector field, I'll just plug in 1 for x and 1 for y into the f and g recipes. So I get 1 minus 1 times 1 on the top and 1 times 1 minus 1 on the bottom. And turns out when those are all 1s, I actually get, for my vector field at that point, 0, 0. What does the vector 0, 0 look like? It's the only magical vector out there that has no magnitude and no direction. Its magnitude is 0, and its direction is, well, I'm not really going anywhere, so I can't really tell you what direction I'm going in. And so, really, I just put a dot there. On top of the black dot, I just put a blue dot. There's no way for me to say it's pointing in any particular way or with any particular magnitude. Oh yeah, remember? I was doing that over here, and I noticed that those were really special points when it turned out that my rate of change became 0. That's what I was calling the equilibrium point, and that corresponds to a time dynamics where things just chill out, and they're kind of like just staying exactly the same for all time. That's what we call equilibria. In the two-dimensional example, that analogy still holds. And so 0, 0 is an equilibrium point in which you have no movement at all. Okay, boy, I wish I had this graph handy, but unfortunately in 2 and all higher dimensions, we're not going to have this graph, which is really too bad because we're going to analyze the shift out of this graph when we get to bifurcation theory. That's right, we're going to analyze the shift out of it. Remember shifts from pre-calculus 1, where you can take a graph and you can vertically shift it up and down, or you can horizontally shift it to the left or right? Well, when we start to play with these parameters, r and k here, that's going to turn into shifts in this graph, and that's going to allow us to analyze the change in the stability and equilibria that occur in our models. Ooh, I can't wait, but we'll have to wait to the next video. I'll see you later.